Okay, cool. Welcome back. We had few, like especially with snow day, like weather's been crazy. And now it's 50 degrees. It's so nice out. So thanks for being here. Yeah. I feel like sometimes we should just cancel class. Like, oh, it's too nice out. UConn's closed. Because it's New England. Like, you need to capitalize on sunny days. But, I don't know. Thanks for being here. We'll do some work anyway. But anyway, so the reason I brought that up with like delays and stuff is I pushed this off so we get like 2 more days to work on it, like Monday and Wednesday, and then Thursday try to wrap up everything and turn in the work that we've done so far. That's my plan, and I think that'll work out pretty well based on how we've been progressing. We did a lot of the hard work of the kinematics of figuring out how things are connected and how they move. That's done. Now we're moving on to kinetics of like, as we're applying, we have this load F pointing down. What is our screw actually holding? Like how much load is in the screw? That gives us a lot of information about like how much friction is in the threads and like as we're turning this, like how much torque do we need? So that's where we're at right now. Sound like a plan? I'm just pausing for questions or changes. All right, that's it. Saddle up. Last time, is it coming up? This was free body diagram that we came up with. So, what does that tell us? What do we know from this free body diagram? Does it tell us anything? How do we use a free body diagram? Like, what are the equations that it gives us from forces here?
Like solve for like the forces, like the X and Y.
Yeah, so we could sum up these forces, right? We could say sum. Typically we use like X and Y. We can use other sum of the forces, like we could change the coordinate system if we wanted. Here doesn't make a lot of sense to like introduce a whole new like diagonal coordinate system, but you can. You're the engineer, you can choose anything you want. So we get those 2 sets of equations. There's another one that we can use too. What's the other one? The moments, yeah. We can look at like what is the sum of the moments. I'm gonna put a little question mark there. What's different about moment versus force? Yeah.
The moment's only like a force times a distance, so force distance.
Yeah, so it's a force times a distance. What distance do we use for the moment?
Perpendicular distance
Perpendicular to what?
from like the spot to the floor.
What spot?
Going down through the cross.
Yeah. So what spot?
Whatever one you choose.
So you can choose anything you want? Is that always true? I know when someone says, is it always true? It's like, well, then you come back with, it depends. But can you always just choose any point and say, this is my moment? Like, this is where I'm going to sum the moments.
You usually want to see like a actual point, so like where the screw is or something that can actually.
Yeah. So in general, yeah, choose any point you want. There are spots that make it more difficult and spots that kind of help a little bit. No matter what, you still got to do some trig, still got to do some math. So we can choose any point. This is dynamics. What is the sum of the forces equal to? F equals what? MA?
Should be 0 if nothing's moving.
But everything's moving. We already said that we want everything to move, right? So F equals MA. I mean, that one we can't break. We can't say that F is not MA because we don't feel like MAing it. But there was the idea that it's still equal to 0. Why would it still be 0? Could we still say it's 0?
You say like at each moment, like second is station. It's not like falling apart. So there's no.
It's not, okay, not falling apart, yeah. So in each step, maybe forces add up to 0, but it's definitely moving, right? Yeah.
If the velocity is the same, then the acceleration would be 0.
Okay, so one thing is that if our velocity is not changing, then it's got to be sum of the forces is 0, because A is telling us changes in velocity. We already figured out that, coming down here, one thing we figured out is that velocity is changing. So it is changing. So we do have acceleration. So here is your vocab word for, and this is a great, just put it in your pocket, pull it out anytime in the future when someone is telling you to do dynamic analysis. It's a quasi-static analysis. And you say everything's equal to 0, you're not saying that it's not moving, and you're not even saying that acceleration is 0. What you're saying is that the changes in momentum are negligible compared to all the other forces. We have the weight of a car pushing down on this thing. The acceleration that it takes to move this thing from 1 millimeter per second to 2 millimeters per second is not going to change like the loads that our screw or the loads that we need to apply. Does that kind of make sense? Like everything's moving so slow compared to the loads that are applied. So it's a great, use this anytime somebody's like harping on you about like, oh, well, didn't you consider the Coriolis effect in your analysis? It's like, dude, it's a quasi-static analysis. Back off, I'm a scientist. So quasi-static, put it in your pocket, save it for later. Or save it for now, quasi-static. The nice part is it just turns into a statics problem with motion. In statics, we know how to do it. The motion, we figured out how to do it. And then we'll figure out the rest. Okay? So let's try a quasi-static analysis. What can we figure out so far from our free body diagram? You can write it down, think about it. What do we got so far? Talk about it. They all equal each other, right? There's too much symmetry right now. It's not actually telling us, at least left to right. Yeah, okay. That sounds good. What are you doing so far?
left and right, like the reactions and the tension like should cancel each other out. So like I'm trying to go back to the static, it's like problems.
Yep. Yeah. That's a good starting point. Not sure? Okay. Do you know what which vectors are just along the x direction?
Yeah.
Which ones?
RX and T-squared.
Okay. And what are they at? Alright. So really we just have an equation of 0 to 0.
Right.
It's not too helpful. What about vertical?
Forces gotta be basically one half of the force of the
Yeah. All right, so one thing we figured out was that for every positive x thing we have a negative, at least in the x direction. We have some things pointing right, some things pointing left, but we already said there's symmetry, so they're equal enough. So at least x component says 0 equals 0. Not super helpful. What about our y component? Does that tell us anything?
It's that negative f, the negative f is equal to 2n. If we're using like a regular equivalent system.
Yeah. So we can say n, at least the reaction force on either side, like on both of those bolts, that's F over 2. That's a good start. That one makes sense. Like if you're lifting a car, you need something to push off of. So we're pushing off the ground. The ground has to hold up the car, no matter how fancy our jack is. Moments, did we try anything here? You did? Did it come up with anything?
Well, since we have, like, we can solve for n of this, but I think we have force, you can solve for t of this screw, even though it's gonna be like t squared times the distance, which is to the angle.
Okay.
Triangle,
Yeah. Did you come up with,
equation.
yeah, like any equation?
T screw times whatever that distance is, minus t screw times whatever that distance is again,
Yeah.
plus n times, I put d2, which is gonna be like the distance between,
Okay. Yeah.
like, yeah, and then force is.
Because we were just saying how it's got to be that like perpendicular distance. So it's sort of T screw, both of those, both the positive and negative torque are going to cancel out. Yeah.
What are we taking the moment of?
That one, at least what I was showing here is like this free body diagram, even though we included a bunch of forces, like it's accurate, but it's not helping us get to the next answer, right? Like we need something more. And so in this case, whether I choose this side, a 1 or a 2, both of them are going to have like torque from T screw minus torque from T screw. So overall, total torque is 0 around either of those points. Okay. So what do we do? What did you do in statics? Like, what's the next step when you just come up with 0 equals 0? Yeah. Yeah, like chop it and then start looking at what are the forces there, right? So you can go nuts with this and split it up into every different component if you want, or we could start off with like a couple of things, like just the right half, same that we did with like kinematics. I'll try just the right half. Is that all I need? Yeah, so something like the hinge. Where am I? This hinge still has a force on it. Like there's something preventing the car from crashing through it. There's got to be some kind of reaction forces there. So it's a hinge. Every hinge has an X and a Y component to it. So let's just write it as kind of something like this. Like a BX and a BY, something like that. I guess really downward would be better for that BY component, but somehow, there's got to be something there. Do we know what that BY is to start? Yeah.
Wouldn't it be
F over 2? How does that sound? Sounds reasonable, right? And like if you're not sure, then we draw the free body diagram of the thing being supported. And sure enough, BY and BY both have to be 1/2 of that. So here I could redraw all that as like F over 2. Cool. How does this look? There's less, well, there's more stuff going on because now we're starting to look at internal forces on our free body diagram, but a little easier to get at, like what is that tension in our screw? How much force is on our screw? So let's try this one. And we can still say they're all 0. It's not that it can be 0, but it could also be something else, like if you think about push, if you have this like thing which is pushed down on it, there's got to be some load transfer out this way, and then you would get it out into that thing. This thing pushing on it that way. So if it wasn't there, like if there was 0 force, then it could fit it on itself. So something. It's not that it's always not zero, but in general.
There's no big difference here.
Yeah.
I also think it's when there's no like external forces in the institution.
Yeah.
Two.
Yeah.
Two jigs.
Okay. Yeah, that makes sense. We already solved for Yeah.
We don't have M, we have M. We have U. We already have Yeah, you can choose any of them. Alright.
I mean, you can even choose, you can be like crazy and choose over here and then there. Yeah. And it's not gonna change the equation that you get from it. It's not gonna change. You're still gonna get the same relationship. Like if you choose this one.
That is the overall. That was no also.
Okay.
Let's try it. We don't have
Which spot did you choose?
Oh, I chose.
Okay. Yeah, yeah. So it's got to be like perpendicular. This is BY.
Okay, so what is that? Okay, that's what I was.
Yeah.
Pretty sure it's BY, but it's very careful for that.
Didn't want to try moments.
Moment, like, is it, like, T, the screw, or like, and then we have to go with like an angle?
Yeah. I mean, either way, somehow.
Okay.
Yeah, let's have a little moment. A review. All right, quick little moment of like what is a moment. Formal definition is that M is like, so if I say like M of O, here's my O, here's my point P, so I have like a position of something and a force applied to that point. Here Usually it helps me to think about like using a wrench, just because that's something that I actually do, like rather than just like the theory of like, this math solution. So first off, if I have a wrench and I'm like pulling up on it like this, is this creating positive torque or negative torque? Positive or negative? Am I threading in or threading out? Positive? Yeah. So somehow it's kind of like taking this thing, threading this way. So screw is coming out of the page, or unthreading, at least if we have right hand thread. If someone reverse your threads, then now you're dealing with like, I don't know, some weirdo, someone who's trying to make your life hard. So here, decreasing tension on the screw, or unthreading it. And so the formal definition is R cross F, like a cross product of these two vectors. So it's like creating a parallelogram, right? Do you remember this from multivariable calculus, that a cross product is describing the area of this parallelogram of those two vectors? So super fun. But let's turn this into, so let's say F is, we need positive, so let's say it's 2I plus 3J newtons. R of P is 3I plus 1J meters. A big honkin' wrench with a tiny force. It's like a 4-meter wrench. That's pretty darn long. So really what we're saying is, when we do this cross product, it's like we have this Rx, this Ry, this Rx, then we have an Fy and an Fx. Is the Fx creating torque along the x direction? Like if I only had Fx and the thing was, here's my Rx, Fx. Is this creating torque? And it'll catch up in a second. Does this create torque? No. The Rx direction has to have the Rx and the Ry have to have like perpendicular components. And someone brought that up earlier, of like you have to take the perpendicular distance to what you're talking about. So x times y times x, and the general math way of doing that is the cross product, figuring it out that way. So what is our total torque? What's the total torque here? I'm taking RP cross F, 3I times 2J, sorry, 2I, 3I times 2I. Sorry, that should be an Fx. I just didn't draw. Yep. I just didn't finish drawing the x. That's a good question. Yep. All right, so 3i times what? What's our first thing? What's our first value? 3 times 2 or 3 times 3? Less? It's 3 times 3, like I times j, the I component, j component. Is this coming back? I know I say this a lot in this class. This class is not, the concepts are something pretty familiar. F equals ma, you've dealt with it a lot. The difficult part is that you need to apply, I don't know, 4 or 5 different like classes. Here we're dealing with like multivariable kind of vector analysis, differential equations, vector, like there's all these different things that all come into like, oh yeah, just, bang it out. Just do the dynamics, F equals ma. So it's okay to feel like, I don't know this, I don't remember this, because most of the time you don't have to. It's just one domain at a time. Here it's like, do everything, everywhere, all at once. All right, so our moment is 3 times 3 I cross j plus 1 times 2 j cross I. So it's 9, is it 9 plus 2? This one's tricky. It's got to be a subtraction. Yeah, which one gets subtracted? The 2. What I like to do is, if I have like components like this, is write out ijk in a circle. If I'm moving clockwise, then it's positive, and if I'm multiplying counterclockwise, it's negative. So anytime we have like in plane, everything's like 2-dimensional xy, we'll always end up with torque in the k direction, like out of the plane. But it could be positive, could be negative. Yeah.
I did it like the table way where you have like I hat, negative j hat, and k hat.
Oh, okay. What did you get?
I just got the negative version.
The negative?
Yeah, I got negative stuff.
All right, so you did I, J, K, and then R cross F, right? So 3, 1, 0. 2, 3, like this? Did you do F cross R or R? Did you flip the rows? That's good. So if you do an F cross R, you should end up with the negative of the R cross F. But that's okay. Yeah. Is this how, I've seen this one a lot, like a lot of people use this table or this determinant to figure out what is a cross product. That one works. I find this, they're equivalent of like writing out the components and doing unit vector cross products versus like writing out the whole determinant. I avoid like doing big 3x3 determinants just in general. It's a life choice. I don't know. All right. And I brought that up because a lot of people were avoiding this moment equation. Like, I'm not sure. But we got this. All right, sum of the forces X, we have Bx minus T of the screw minus Rx. So nothing like solvable yet. Didn't tell us what Rx is. Y, we have F over 2 minus F over 2. 0 equals 0. That makes sense because we already solved for what that normal force was, so it still needs to add up to the same value. Where do you want to take moment around? O, so I like O at the bottom, A is on the right, B is at the top. Where'd you go? Where do you want to go?
I did
A, and then O. They're all like, it's not changing the location is not going to give you a different equation. So we'll try. Yeah, which one do we want to do? I kind of like O to not to say like A is not good. A is good because there's like some symmetry involved. O I like because there's less things with moment applied. So I'm gonna do O, but you'll find, but what we'll see is that we're still getting the same like system of equations out of it. So how much torque does Rx have around O? 0. So 0 from Rx. What about the bottom F over 2? Also 0, because moment arm, if the position's 0, can't create a moment. All right, so those are good. How about the tension from the screw? How much moment does that create? We probably need our angles back in here, right? L cosine, so like that vertical distance, right? Yeah. Yep. All right, nice. So L cosine theta times T screw, TS. I'm just going to leave it as TS. Is it positive or negative? Positive? Yeah. Thumbs up. Out of the page. Out. Okay, what about for the top B, F over 2? How much torque does that have? 0, but it's not 0 displacement. Why 0? It's definitely far away.
It's on the same like axis.
Yeah, we have a negative F, we have that F over 2J, and then our distance is only 2L cosine theta J. So J cross J is still going to be 0. All right, what about BX? That top BX, how much torque does that want to create?
It's going to be negative 2L cosine theta BX.
Yeah, times that BX. So that same distance to get up to B, but now it's an actual like torque being applied. And we're calling it negative because at least the way that it's drawn, it's going into the page. Torque is going into the page. Other way to do this is like, it's a J crossed with a positive I, so then we end up with negative K. All right, so we're done, right? We solved it. Now I gotta get this down out of our moment. So do we have an answer? No? Why not? How many unknowns do we have?
Actually, I'm not sure about that. So that last class was something about the RX being zero. Why? But is that only true of like the median equation because they cancel each other? Is that what you're saying?
Yeah, that Rx, so a negative Rx plus a positive Rx has to be 0.
Okay. I should
and-
say it's like the actual force itself is going to be zero, but that makes sense.
And this is a great clarifying question because it came up earlier of like why did I include if there's no external X direction force, why am I including these like BX reaction force? Like, shouldn't they just be 0? And if you think about like, if you have this structure and you push on it, like as I push that F/2 down, that top link is going to want to fall to the left. So there's got to be something supporting it. Same thing here, that this one is going to want to like fling up that way. So there's got to be something keeping it there. So it's not that it can't be 0, but in general we have to say we put a pin there, that pin is creating 2 forces on it. So we don't know Bx, we're trying to solve for T, we don't know Rx, but we have 3 equations, only 3 unknowns. Should be fine, right? One of our equations is 0 = 0, which is not so helpful. So really we have 2 equations with 3 unknowns. So take a second. There's 2 different approaches you can take here. Take a second, just kind of brainstorm where do we go from here? Because we're kind of stuck. 3 equations, 2 unknowns. There's no way to like just solve that outright. So what's the next step? What else do we know about the problem? What else can we do next? There's like a brute force way and then kind of a intuitive way. Okay, something from like the first, like the bigger one?
Yeah, but find one of these solutions and send it to the
Okay. I was gonna try to plug it back into the bigger body. Okay. What does that do? Represent that? Okay.
When is the second case problem due?
This one, it was gonna be Monday, but pushed it off, so we have like Monday, Wednesday, and returning Thursday.
Okay.
Where do we go from here? What's the next step?
I don't know.
You don't know? We ran out of that. We've got plenty of I don't knows up there. We need some I knows.
You know what else?
What are you doing next? What would you do next?
I'm trying to think of a way to combine what we have between the moment equation and the
Yeah, I mean, like you can,
well, it's like you said, it's like you can force it that way.
but it's still gonna leave you.
With another, you still won't be able to find all the.
Yeah, like with 2 equations, you can't solve it no matter how you jump them. Yeah, so kind of stuff out. Let me think here. I mean, you can do that, but it's still gonna tell you TS is the same TS is EX over 2, right? You have
But if you take the moment of the
yeah, similar difference between them there. You'll still, they're both.
that is the if you like you swap out EX for a ratio of TS,
Yeah.
couldn't you reduce it to 2 variables? Couldn't solve it.
You're still gonna have like this ratio in there. Like it's still gonna be these variables. They're still can't solve
Last day.
So we know from the equation, we can find that cosine divided
It's just
but it doesn't tell us what LS is. If there's tension and react that RX is reaction. Why am I gonna go through the tension? Always fun to have YouTube on.
Yeah. You've got to like open up like a PayPal account so we can start sending donations.
Oh yeah, that's true. Start monetizing
Yeah.
my lectures. Yeah, at a Patreon. Like,
Yeah.
what's up, fans? All right, people are stuck on this. I think, for the most part, ideas that I've heard are like somehow rearrange these two equations and somehow we'll get something new out of it. Any other ideas? Yeah.
I have two ideas. I don't know if it works, but you know, still like sort of global evolutions of it, and technically T, like 2T screens 2RX, or actually, that should be right. Actually, never mind, scratch that. But my other idea.
Okay.
Because you could slice it, technically can't you slice it again, like it doesn't matter how many times it's on the choice there's something.
Yep.
You just solve for like whatever forces you need, and then plug them into the equations we have now, and then solve the rest of the equations.
Yeah, so one way that we can do this is like when we split it once, we introduced new variables, but we got better equations, like we got a little closer. We can keep splitting this into as many parts as we need to. We can even look at internal forces like inside the beams themselves to figure out like how much moment, how much tension. So that's one approach is split it up into those two, into the top and the bottom, and start looking at forces there. Called B and T. Another one is that because everything is supported by pins, we're not applying any moment to our structure. Does that make sense? Like each beam is either under tension or compression. So what does that tell you about like the forces in the hinges? Does it tell us anything about it? Like the reaction forces that our hinges are creating?
Can you repeat that?
Sorry?
Can you repeat that?
So should we minimize? Now it's gaining traction. Now, like, for the algorithm, I've got a lot of engagement now. Sorry. So the question was, in these pins, like here, when we're looking at Rx and F over 2, do we know anything about those two forces? About like the resultant force of Rx plus F over 2?
Are you saying that it's like supposed to be zero because it can only move, like it doesn't move in the problem?
That it has to be 0? Well, the result, so it's not so much because they're two perpendicular forces, so we can't like add one.
They're equal to each other or something?
So they could be equal to each other, but it would depend on like where the beam is, right? Of like where that link is facing.
If you're saying the resultant force, then you just do the perpendicular.
Yeah, we add, so if we add like F over 2 plus Rx, then there's a direction to it. Do we know what that direction is? Squared? Something squared. It's always squared. All right. So the second way is that I know I can't have a resultant that's not along my beam because the hinge is not creating like a torque. Like it can't like hold any force other than directly along that like beam this way. So those are, if we use this, it gives us like one more equation that like, if this is my theta, what is that? The opposite. We have like another equation that opposite over adjacent, the direction of my resultant has to be in that direction. So either way, whether you keep splitting it up further is kind of like the brute force, you'll definitely get there. It will always work. Another way is that because we have hinges, we can say like at every hinge, there's no moment applied, so the total force at every hinge has to be equal to 0 too. Or, well, not equal to 0, but like the reaction from that beam down onto the hinge has to be along the direction of where the beam is. So either way, try it one or the other or both. Cool. All right. Then that's 2. We're out. We're good. What is happening here?